Hello everyone. We are going to start with potential function and stream function, which is a continuation of kinematics of fluid motion. So straight away let's go. We'll define these functions. So before that, you know all this, that is acceleration components and then velocity components. We'll quickly revise this and then we'll go ahead with the new things. U, the component of velocity in x direction, dx divided by dt. P, the velocity in y component, dy, the distance traveled in y direction divided by dt. Similarly, W, dz by dt, the distance moved in z direction divided by dt. The total velocity, you know that it is ds by dt, which is given by v is equal to ui plus vz plus wk. Acceleration components, already we have done this, which is given by ax du by dt plus du by dx into dx by dt because of chain rule. Okay. Similarly, other components already you have seen. The total acceleration is given by component in x direction and the direction vector, and then component in y direction vector, component in z direction and direction vector. And if you want the magnitude of acceleration, it is square root of ax squared plus ay squared plus az squared. Here if you substitute for dx by dt as u and dy by dt as v and dz by dt as w, you will be getting a slightly different form that you can just see. It looks better also. I think I have made use of these abbreviations in the last session while solving a number of problems. So ax du by dt remains the same. So instead of dx by dt, I have substituted u. And then instead of dy by dt, v, dz by dt as w. Likewise, I have done everywhere. Only thing is, instead of putting it that side, if I put it before, it reads like ax is du by dt plus u into du by dx plus v into du by dy plus w into du by dz or dz. So ax, ay, az components will be having du by dt, dv by dt, dw by dt as the first terms. All the three terms will be having u, v, w multiplied with differentiation with x, y, z directions of corresponding. If it is x, u, if it is y, v, if it is z, it will be w likewise. Okay. So with this revision, we'll go ahead. So velocity potential, what is this? It is a scalar function of space and time. That is space and time in the sense x, y, z and time, right? It is a function of x, y, z and time, such that there is a condition. Its negative partial derivative with respect to any direction gives fluid velocity in that direction. So that is what the definition of velocity function means, or velocity potential means. It is denoted by phi or pronounced as phi sometimes, right? So if it is a general motion, unsteady flow, then phi is a function of space, that is to x, y, z and t. If it is a steady flow, then time invariant it will be. That's why time factor doesn't come into picture. So phi is equal to f of x, y, z. And then suppose if it is a two-dimensional flow, then z also disappears. It will be function of x and y. And then if it is a unidirectional flow, then phi will be only function of either x or y or z. So by definition now, what it is, such that it's a negative partial differentiation or partial derivative with respect to any direction. Here I have done minus partial differentiation with respect to x. Dou phi by dou x gives fluid velocity in that direction. Fluid velocity in x direction is u. Similarly, minus dou phi by dou y, if I do, I should get velocity v, and minus dou phi by dou z, if I do, I should get w. So that completes the definition of velocity potential function. Okay. Now here, for steady incompressible flow, already we have derived the continuity equation, which states that dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. This is for incompressible flow, right? For steady condition, because there is a additional term here, dou u by dou t, all that, and then even there is a rho here. All those terms will be disappearing if I put a condition that it is a steady incompressible flow. So this condition or continuity equation, now in this I will substitute u from earlier definition. U is dou phi by dou x, and similarly all other terms, right? So this, if I substitute, what happens is differentiation of that with respect to x of dou phi by dou x, right? So it becomes dou squared phi by dou x squared. Of course there will be a minus sign here. Similarly, everywhere there will be a minus sign. So dou squared phi by dou y squared, because it is a dou by dou y of v. V is dou phi by dou y, of course negative sign, and then w is dou phi by dou z. So it becomes second derivative of phi in x, y, z and direction equal to 0. This whole thing is abbreviated as del squared phi, and this equation is known as, this equation is called Laplace equation. Any function phi that satisfies Laplace equation represents a possible case of fluid flow. This is an important statement, that if phi exists satisfying the Laplace equation, then as a corollary we can say that fluid flow exists. Now, but it can be shown that dou squared phi by dou y dou z equal to dou squared phi by dou z dou y, and so on, which indicates that omega x, omega y, omega z, which are rotational components, which are equal to 0. So that is a flow irrotational. That is, any phi that satisfies Laplace equation is a possible irrotational flow case, since the continuity is satisfied. That is, velocity potential exists only for irrotational flows of fluid, and hence such flow is also known as potential flow. Here there are conclusions. The properties of fluid, properties of not fluid, velocity potential are: number one, if the velocity potential phi exists, then the flow should be irrotational. That is statement number one. If the velocity potential phi satisfies the Laplace equation, then it represents a possible case of fluid flow also. Okay, so this completes discussion on velocity potential function. Next we have stream function. Anyway, the same thing I have written in mathematically, and then found out the equation for equipotential line. Now, what is equipotential line? Here it is an imaginary line through the fluid flow. Okay, I'll try to explain it with a sketch. Now suppose there is a flow here which is occurring, right? Now there is an imaginary line along which the velocity potential phi is constant. Means if we have what shall I say, a line, and there are number of points here, and then every point here is having, one sec, so here there are number of points, and then of course there are number of points, and then velocity potential function for all these points is same. That is what phi equal to constant means. What for all these points phi is the same. So it is an imaginary line along which the velocity potential phi is constant, that is to say phi equal to a constant. Hence differentiation of phi will be equal to 0. But phi is a function of x and y and also z, but in two-dimensional flow it is x and y for two-dimensional steady condition. Hence d phi will be written as dou phi by dou x into dx because of the chain rule, dou phi by dou y into dy. Substituting the values of u and v, we get d phi equal to this. On the left hand side it remains the same, d phi equal to dou phi by dou x is u, right, of course minus u, that's why it is minus u into dx, plus dou phi by dou y is minus v and multiplied by dy. So from this we can say that u dx is equal to minus v dy, or dy by dx is equal to minus u by v. That's an important equation that we have arrived at, which is dy by dx is the slope of equipotential line, equal potential, that's why it is equipotential line, means phi is same or it is not changing. In the curve which is called as equipotential line will have a slope dy by dx which is equal to minus u by v. Okay, as I told you, stream function. Now this is another function we have in fluid flow, stream function as well as velocity potential function. Stream function definition is, it is represented by psi, pronounced as psi or psi. This stream function is defined as the scalar function of space and time. Again you can see here it is the psi is function of x, y, z and t, right, such that its derivative with reference to any direction gives the velocity component at right angles in anti-clockwise direction, so that the to that direction for two-dimensional flow. Now for two-dimensional flow I have shown psi is a function of x, y and t. For unsteady condition, because time is also becoming a dependent variable, if the function is independent of time t, then psi is function of x, y only, then it is steady condition. Now as per the definition, if I take partial derivative with reference to any direction gives the velocity component at right angles. Now if I take x, right, so dou psi by dou x partial differentiation with respect to x, if I take, it gives you the velocity in this direction, that is perpendicular to that in anti-clockwise manner at 90 degrees, so that is v. Now dou psi by dou y if I do, means partial differentiation with respect to y if I do, it gives you velocity in this direction, right, in this direction, but velocity in this direction will be, in this direction will be v, u, in this direction it will be obviously minus u, that's why this dou psi by dou y becomes minus u. Okay, now comparing the velocity components in terms of phi and psi, it represents like this: dou psi by dou x, dou psi by dou x is v, which is equal to minus dou phi by dou y, and also dou psi by dou y is minus u, which is dou phi by dou x. Now these two equations are known as Cauchy-Riemann equations. When velocity components are substituted in the continuity equation, continuity equation substituted in continuation, dou u by dou x plus dou v by dou y equal to 0 in terms of psi will be equal to, you can see here, dou by dou x, but u is minus dou psi by dou y plus dou by dou y, phi is dou psi by dou x equal to 0. So this gives you a equation something like this: dou squared psi by dou x dou y with negative sign plus dou squared psi by dou y dou x. This indicates that the function is continuous, right? Now further, irrotational condition is used. If we use this condition, it is giving you equal to 0. So this equation is equal to 0 is the Laplace equation for psi. Therefore, a function psi that satisfies Laplace equation represents the possible irrotational flow. Now the properties of stream function are, if the stream function psi exists, then it represents possible case of fluid flow. If the stream function psi satisfies the Laplace equation, then the flow should be irrotational. Okay. Further, line of constant stream function, or it is called streamline, means psi is equal to constant. It is an imaginary line along which the stream function psi is constant, that is psi is constant. So d psi will be equal to 0, but psi is a function of x and y for two-dimensional conditions. So d psi will be equal to dou psi by dou x into dx, dou psi by dou y into dou y. Substituting the values of u and v, we get, you can see here, dou psi by dou x is v. So this d psi is here, this is becoming v dx, and dou psi by dou y is becoming minus u dy equal to 0. So this becomes phi dx equal to u dy, or dy by dx becomes v by u. So this is equation number 2, where dy by dx is the slope of the streamline. Now, so together if you look at, streamline is represented by dy by dx equal to v by u, and then those are if phi is constant, then it is equipotential line given by dy by dx equal to minus u by v. So this is slope of that particular line, equipotential line. This is slope of streamline. What is equation of the line itself? It is of course it is a differential equation as indicated here. D psi is equal to dou psi by dou x into dx, or d psi equal to phi dx minus u dy, or d phi equal to minus u dx minus dy. So these two are called equations of streamline, equations of equipotential line. Now from equation 1 and 2, this is 1 and this is 2, if you just study, this is also slope, this is also slope, but one is minus of the inverse. Or if you multiply the slopes m1 and m2, you'll be getting m1 m2 equal to minus 1. What it indicates? From equations 1 and 2, we get that product of the slopes of equipotential line and streamlines is equal to minus 1. Thus, the equipotential line and streamlines are orthogonal, perpendicular to each other, right, at all the points of intersection. That is what the final statement as far as streamlines and then equipotential lines are concerned. Okay, relation between stream function and psi function, already we have done this. Both d phi by dx equal to d psi by dx minus d phi by dy equal to d psi by dx. This is Cauchy-Riemann equations. Okay. Now there is a flow net, that is grid of equipotential lines and then streamlines put together. It is called flow net, right? So a grid obtained by drawing a series of equipotential lines and streamlines is known as flow net. The flow net is an important tool in analyzing two-dimensional irrotational flow problems. A grid obtained by drawing a series of streamlines, psi lines, and equipotential lines, that is phi lines, is known as flow net. The construction of flow net, that is C phi lines, is restricted by certain conditions. What are those conditions? The flow should be two-dimensional strictly. The flow should be steady. The flow should be irrotational. The flow should not be governed by gravitational force. Okay. So this is about definition of the flow net, etc. So if you look at the flow net, how it looks is quite simple. If you have number of say equipotential lines like that, let us say, then the flow lines would be at the intersection, it has to be perpendicular like that. So if I start drawing here, it should go there, so it should go there. So I'm sorry, this would have been something like that. Yeah, this is wrong. Okay, this is flow line, this is flow line, this is flow line. Okay, so anyway, here types of flow net, uses of flow nets are to determine uses of flow net are to determine the streamlines and equipotential lines, quantity of seepage, upward lift pressure below the hydrostatic structures, hydraulic structures like dam, gates, etc., velocity and pressure distribution for given boundaries of flow, the design of streamlined structure, flow pattern near wells. So these are the applications of or uses of flow net. Okay, we'll solve some 2-3 problems. Problem number 1, it's given for a two-dimensional flow, psi is given by 3/2 y squared minus. So it is a scalar function, right? Psi is given by 3/2 y squared minus x. So it is a function of x and y. T is not there, z is not there. Determine velocity components at the points 1, 3 and 3, 3. Also find the discharge passing between streamlines passing through the points given above 1, 3 and 3, 3. Okay, here psi is given, right? Now velocity, if I want velocity u and v, right? U is minus u is given by dou psi by dou y, if you remember, right? And then v is given by dou psi by dou x. Okay. So dou psi by dou x is v. I'll differentiate this with respect to x, that gives you v. So 3/2 constant is outside, this term disappears, and then it becomes minus 2x. So to say v is minus 3x. Okay, now at 1, 3, that is velocity v, velocity component v at 1, 3, if I substitute, it will be minus 3, and velocity component v at 3, 3 will be minus 9 units. Okay, now dou psi by dou y, that is minus u, is equal to, so minus u is equal to differentiation of this with respect to y. So 3/2 into 2y, so this becomes u equal to minus 3y. Right, this indicates that u is equal to minus 3y. And now if I want velocity component at 1, 3, it will be minus 9, at 3, 3 it will be minus 9. Now to find the flow, we have found the velocity components at 2 points, right? If you want a resultant velocity, it will be different, because you know that it is the same point, and we have 2 components, one here and then one here. So if I try to draw, velocity v is minus 3 in the sense it is downwards, minus 3, u is minus 9, so to say it is that way, 9. So resultant velocity, if I try to draw equivalent diagram, so it will be something like that. So that is how the velocity at point 13. But if you want velocity at 0.33, now here there is a value, here also there is a value. I mean, here there is a value. Now if I try to represent that at 33, it is minus 9 is this way fine, and then x component is also minus 9, so it is also like that. So resultant velocity will be in the same manner. Okay, now u and v components are there. Okay, so which will be giving you resultant velocity. Now if I want to find out, also find the discharge passing between streamlines passing through the points 1 and 3. Now look here, I'll put a point 1 3 here, let us say, and this point is, let us say, 3 3, and what happens is there will be a streamline which is going that way passing through point 1 3. There is a streamline which is going this way, let us say this is 3 3. Now whatever flow is there here in between the streamlines, it will be calculated as, say this value is psi 1 and the value at this particular streamline is psi 2. If I find out the difference between psi 1 to psi 2 or psi 2 to psi 1, that will be giving you the flow. Now how do you find psi 1 at point this? So at point A, I have called it as point A. This point is called as point B. Okay, psi at A, which is 1 3, the point is 1 3. So coordinates of these points, I mean this point is given to be 1 3 and coordinate of this is given as 3 3. Now psi at A 1 3 is equal to 3 by 2, because I know psi is given by this equation, this whole equation. So here I will substitute the value of 1 3. So if I substitute 1 and 3, I will be getting 12 units, that is psi at A. Psi at B, if I substitute, I will be getting 0. So at this 12, at this 0, psi 1 minus psi 2 will be nothing but flow that is occurring between line number 1, streamline number 1 and streamline number 2. So therefore discharge passing between two streamlines, psi 1 minus psi 2, which is equal to 2, equal to 12 units. Okay. Okay, problem number 2. Here what is given is, in this problem, u is given minus x, v is 2y, omega is 3 minus z. Find out equation for streamline at the point 1 1 1. Equation of streamline is given by dx by u equal to dy by v. Of course there is one more, dz by w, and dz by w it is given, right? Now here we don't have that third coordinate, because of that it is only a 2 coordinate system, that is 2D flow. Okay, now we'll start the equation for potential line is given by, potential line is given by, if you just recall or go back to the pages and see, it is dx by u is equal to dv by, here it is written dx by u is equal to dy by phi. Now u I'll take it from here, phi I'll take it from here, and then write dx by minus x equal to dy by phi is equal to 2y. Now to solve this, simply I'll take a integration. So this minus is outside, log to the base e x. This half remains as it is, dy by y will be log y, plus a constant of integration, call it as log c. Okay, now further this minus can be taken inside, because of that it will be log to the base e, but it is x raised to minus 1. Similarly, log y raised to half, it will be there, y raised to half into c, because the log of this is equal to log of this plus log of this, that is expanded version. Now on both the sides you have got log, because of that x raised to minus 1, which is 1 by x, is equal to c into y raised to half, or c into root y. So at 1 1 1, a point is specified here in the problem. If I substitute 1 by 1 is equal to c square root of 1, c is equal to 1. So what happens is 1 by x, 1 by 1 is equal to c root of c equal to 1. 1 by x is equal to root y. So from this I can write this. So equation becomes x root y equal to 1. This is the equation of potential line. Okay. Now second part, dy by y or dy by v is equal to dz by w. If I substitute and simplify, I will be getting 2 root y is equal to 3 minus z, and that's equal to 2 by x. So that completes the finding out equations for streamlines. Okay, if u is given by this, v is expressions are written, represent velocity components of 2D incompressible flow, then show that it is a possible case of a rotational flow, and get psi and find phi. Okay, here there are three things that we have to find. First of all, we should show that it is a rotational flow, then find out psi, find out phi. Okay, we'll go. U is given anyway, it is written here, right, and it is differentiated rather, dou u by dou x, right. So it will be dou u by dou x. If I differentiate this term, first term goes off, 2x becomes 2, minus remains as it is, this becomes 2xy, right. So it will be equal to 2 into bracket 1 minus xy. Now phi, if I take and differentiate y with respect to y, dou phi by dou y, it is 2xy minus 2, and this is 0. So it will be like this. Now what happens? Both terms are same but with negative sign, indicating that dou u by dou x plus dou u by dou y, dou v by dou y is equal to 0. Now what is this? This is nothing but continuity equation. Therefore it is possible case of fluid flow. So if the equation satisfies the Laplace equation, it indicates that it is a possible case of fluid flow. Now the flow is in xy plane, so but is there any rotation about z axis that you have to find, right? Now evaluate omega z or omega z. Now z is given by half, two ratios, z, x and y. For y you have to put v, for x you have to put u. So anyway, this expression, if you remember in any manner you want, you just calculate the value of these and then put them. So here dou v by dou x, if I calculate dou v by v is over here, dou v by dou x, if I calculate y squared minus this term vanishes, it will be 3x squared. So that is to say y squared minus x squared, and I want dou u by dou y. If I try to do that, dou u by dou y, again this will be y squared, and then it will be minus x squared, because this term vanishes, differentiation with respect to y, minus x squared. So here it clearly indicates that dou v by dou x is y squared minus x squared, whereas dou u by dou y is y squared minus x squared. That's why the omega z expression half this minus this, if you put these values there, it's equal to 0. Hence it is irrotational flow. Okay, to find out psi function, what should I do? We know v is given by dou psi by dou x, and phi is already calculated. V is given, dou psi by dou x, right? This is directly by the definition of psi function. V is dou psi by dou x, and if you want u, it will be minus dou psi by dou y. By definition, I am writing v is equal to dou psi by dou x, but v is this whole expression. This is dou psi by dou x. If I take x on this side and integrate, what happens is integrating will be giving you psi equal to integrate with respect to x. So it will be x squared by 2 into y squared minus 2xy minus x raised to 4 by 4 into 3, 12, plus some function of y, because when you differentiate with respect to x, even this becomes 0. So this will have to be taken when integrating. This is an important extra term that one has to wisely introduce. Now differentiate psi. Here there was a differentiation of x. Here I'll differentiate with respect to y, dou psi by dou y. So what happens here is dou psi by dou y, if I do for this, because psi is already known, x squared remains as it is, 2y it becomes 2 cancels, you will be getting x squared y. With respect to y, if I differentiate, it will be minus 2x, it will be 0, and f of y becomes f dash of y. But what is dou psi by dou y? It is nothing but minus u. Now I'll put it that way. Minus u is all these terms, minus is minus y cube by 3 minus 2x plus x squared by y. This is dou psi by dou y equal to minus u. Okay, u is here, right? Minus u is minus y cube by 3 minus 2x plus x squared y. This dou psi by dou x I have put there as f dash of y. You can see that from all that f dash of y becomes minus y cube by 3. So integrate to get f of y, that will be giving you minus y raised to 4 by 12 plus c, numerical constant, but it will be always taken as 0. So you have f of y as minus y raised to 4 by 12. Now this is again put into this so that you will have full-fledged expression of psi. Full-fledged expression of psi, if I write psi equal to x squared plus y squared by 2 minus 2xy minus x raised to 4 by 12 plus, here we have just put arbitrarily f of y, but we have concluded f of y as minus y raised to 4 by 12. If I substitute that, plus c is taken as 0. So this becomes expression for c or psi. Okay, now if we want to find out phi, the definition of dou phi by dou x is minus u, dou phi by dou y is minus phi. The same thing we'll use. Exactly similar procedure as we have done for psi function will be done here. Okay, what is that? Dou phi by dou x equal to minus u. U is here, it is put minus. Okay, now integrate with respect to x. Phi is equal to y cube by 3 into x minus 2x squared by 2 plus x cube by 3 into y plus f of y, because if you differentiate with respect to x, we should get this. Now here this is differentiated with respect to y, dou phi by dou y, which is nothing but minus v. Now this is equal to, now if I differentiate this with respect to y, what will be 3y squared and 3 cancels off, so minus it will be xy squared, this will be x squared, this will be vanishing, right? You'll be having x cube by 3 only. Is it right? Something is wrong. Yeah, here I have gone wrong. Like differentiation of y, this first term is fine. Differentiation of this with respect to y should give you 0 here. Should give you 0 here. This is 0. Differentiation of this 3. Differentiation with respect to y, dou y, x cube by 3 is fine. F of y becomes f dash of y, right? So I think here I have written it properly. Minus xy squared plus x cube by 3 plus f dash of y. Here there should have been f dash of y also, because differentiation of phi with respect to y it is. So there is f dash of y that is taken here, should be equal to dou phi by dou y is what? Dou phi by dou y is minus v. So all these terms with negative sign is put here. So you can just see here, this cancels off with this. This cancels off with this. I'm sorry. This doesn't cancel off. Yeah, x cube by 3 cancels off. I'll be left with f dash of y equal to 2y. So f dash of y equal to 2y. That is what I have got. Then f of y, that is integrating 2y squared by 2y squared plus c, numerical constant, which is taken as 0. Then resubstitute this f of y back into this equation. That is an important step that one has to follow. So this f of y is back substituted into this to get phi. So phi will be equal to minus xy cube by 3 minus x squared plus x cube by 3 into y, x cube y by 3 plus f of y, which is found as y squared. So that gives you the final expression for phi. Okay, I think with this we'll stop. Thank you.